I've been a BOINC volunteer for many years, since when World Community Grid was introduced, and my father was working at IBM. And when he was back home, one day he showed me his computer running a simulation for diseases, and I was really impressed. So I started contributing myself with my computer, and started spreading the BOINC word among my friends. Today I will speak about LHC Atom. That is the CERN project that started in 2004 for the 15th anniversary of CERN. And it was running, and is still running, the 6-track application for beam simulation of the stability of the proton orbits in the LHC accelerator. And from 2011, we started also theory, that is the application for events simulations. And we also introduced a virtual machine called CERN VM for volunteer computers. These are the applications that actually we run. So we have a 6-track, and as I said, it's for beam simulations, and runs native as a BOINC application, so without the need of virtual machines. And it runs on Linux, Mac, Windows, and Android. Then we have a theory application for Monte Carlo events, and runs under CERN VM. So you need a VirtualBox installed and set up on your environment. And for Linux only, you can run a theory native, which is the native BOINC application that does not need a VirtualBox. Then we have Atlas and CMS for events simulations. And LHCb, that stands for Beauty Physics Simulations. These are the running jobs over the last 3 months, and we have a peak here that was the BOINC Pentathlon, thanks to SETI Germany. And these are the numbers of the users with the recent credit higher during 6-track simulation campaigns. And here we can see the contributed CPU capacity that varies both with the number of active volunteers and the temporary backfill with spare grid computing resources. The LHC Atom BOINC infrastructure is made of a server cluster running CERN CentOS 7, a server setup scalable with the load balanced web frontend, a dedicated file upload-download server, alias LHC Atom upload.cern.ch, that is made of 3 file servers currently in use, a storage backend on CephFS, submission assimilation and validation server for 6-track, and a MySQL database on DB on-demand servers. And actually, we run a BOINC server release 1.0.3. And the validation updates, as usual, on our development LHC Atom project. And these are the references of our project. If there are any questions. No. We have 3 different tiers. Tier 0, 1, and 2. So the data is spread also among research labs over the world. Personally, I don't know. Okay.
key.
Are you okay just plugging your laptop in? You're welcome to do that.
If it's got HDMI.
We've got that. Yep.
No.
I talk loud, so I probably don't even need that.
Okay.
Okay. There we go. For people who don't know me, I'm Eric Corpola, Director of SETI at Home at the University of California. Some of you may have heard of SETI at Home. So the first question that we always answer is, why bother with SETI at Home? We've been doing SETI for 50 years at least, and typically we just build a box to do our SETI. It's a spectrometer. We take it down to the observatory and it generates power spectra with just a standard Fourier transform or some other discrete transform that has a channel bandwidth times the channel duration equal to 1. And that's just a standard property of physics or sine waves or quantum mechanics, depending on how you want to think about it. So for narrowband signals that you might expect would be coming from ET, you want a narrow channel because that includes the minimum amount of additional noise in addition to the signal. And we'll skip that formula about how the sensitivity varies, but basically the minimum flux is proportional to how narrow you can make that channel. But signals are not frequency stable. If you've got an ET transmitting, even if he's correcting his signal to make it perfectly stable in the center of rest of the universe or of the galaxy or of his star, the Earth is moving, so that signal is going to drift in frequency, and we have to correct for that if we want to do a long integration. So there are a couple of presumptions in this. One is that we're looking for a continuous narrowband signal. Of course, ET might be doing something entirely different. If he's trying to send us any information, the signal is going to have some width that's proportional to the bit rate. But we really don't know what the form of a signature from an extraterrestrial is going to look like. As I mentioned, the Doppler drift limits the amount of frequency resolution you can have and therefore the sensitivity. And as a signal propagates through interstellar space, charged particles interact with it and delay the low frequency portions of the signals, and the high frequency portions will arrive sooner. So you get a limit also because of this dispersion. So this means that any system that we build that we can take down to the observatory is probably going to have a problem in that it's going to do some sort of integration, and it's going to make us insensitive to certain types of signals. The solution to this is, for the frequency shift or frequency drift, is to do what we call a coherent D-chirp. These are two plots of the same signal, and they look horrible up here. And they're kind of supposed to be looking horrible. This is this is a bunch of fast Fourier transforms of a signal. This is actual real data from the Arecibo radio telescope in a SETI at home work unit. there's a drifting signal going through there. And the reason that you can barely see it is it's drifting from one channel to another. The power is getting split between channels, and it looks awful. So even if you shifted the channels to make them line up, you'd lose a lot of the power. If you do a coherent D-chirp, which is basically a convolution of the signal with a sine wave, you can recover almost all of the power back into a signal channel. And that's what SETI at Home does. It does it 59,000 times on a 107-second chunk of data. That takes a little bit of CPU power. That gives us an increase in sensitivity of about a factor of 10 over those systems that we had at the observatory. And even with the new breakthrough listen data recording that they're doing and analysis, we've got about a factor of 10 sensitivity boost over them as well. There are about 100,000 people running SETI at Home. Right now, we've had over 10 million since we started in 1999, the bulk of them before the changeover to BOINC, although it's really a little bit difficult to count how many unique people we had given the system that we had at that point. Those 100,000 people have about 200,000 computers and a bit over 1 million CPUs, about 110,000 GPUs right now, and 20,000 mobile phones running SETI at Home. We crank about 1 petaflop these days. That's a BOINC petaflop, meaning that's what, if you go to the BOINC stats sites, that's what it will say you're doing. Given we're the only project that actually has a conversion from BOINC petaflops to actual flops on the CPU, that's about 360 real gigaflops of actual computing. From this, we get a variable signal bandwidth and time resolution. That means that we can look for very narrow signals and ones that are much wider and maybe have some time variability. We can search for multiple types of signals, and I'll get back to that on the next slide. And our sensitivity is about 3 times 10 to the minus 26 watts per meter squared at the Arecibo Observatory. And the closest thing I can come to on that is a cell phone on Saturn. Yeah, it's not a cell phone at the nearest star, but it's still pretty faint. We look for 5 types of signals. Spikes, that's just a single bin above a given power threshold. That's basically the same thing that our original spectrometers were looking for, only we're looking for it in a bunch of different Doppler drift frames. Gaussians, that's if you've got an object on the sky and the telescope's field of view moves across it, you expect it to get brighter and fainter as the field of view moves through. That's roughly a Gaussian shape. So we do that sort of fitting. We look for triplets, which are 3 evenly spaced events in time over a period range from 3.5 milliseconds to 53 seconds. Pulses, we use a folding algorithm. It's not the same as a fast folding algorithm. Back when we wrote this, it turns out that the fast folding algorithm doesn't cache very well. So and on CPUs with small caches, which is what everyone had in 1999, this actually performed better. That may or may not be the case anymore, but we haven't changed it back since the results are somewhat different. So that looks for pulses on scales from 1 millisecond to 53 seconds. And autocorrelation is a technique where you're looking for a waveform that is repeated. Doesn't matter what waveform, it could be a square wave. If it's repeated, the autocorrelation will find it, even if a straight FFT wouldn't. No one's really mentioned how BOINC works, but I guess everyone knows how BOINC works here. Right now we have 3 primary data sources. Arecibo has been operating for us from, well, we've been using the alpha receiver since about 2006. GBT, we started getting data through Breakthrough Listen there. And right now, both the limits to how much data can get out of GBT and limits to how much we can process limit us to about 1% of the sources they observe with Breakthrough Listen. Parks, we're still working on, and I should probably be back in Berkeley working on this rather than being here talking. Breakthrough is doing a sky survey near the galactic plane. We're getting data from it, but due to the usual snafus that come with new projects, a lot of the headers have inverted frequency axes and things like that. So it's there's a little bit of work to make it usable data. Can we see anything? Again, a horrible graph for this projection system. This is Voyager, and this little faint thing here is one of its data channels. This is the farthest transmitter away from Earth, and, well, SETI at home better be able to detect that. Yes, it detected that about 1 million times in that. Really, Voyager is not all that faint. If it were, it would be hard to get data from it. This is what actually a SETI at home client would actually return from that. It would just detect the first 30 or so events and say, oh, this is full of garbage. We're done. But it still gets the main structure of the data channel. I'll skip this graph because this is really what's important. Interference. Every time we point a radio telescope somewhere, we get obvious proof of intelligence, or at least proof of pollution. We get lots and lots of interference from terrestrial transmitters, from satellites. So this is a frequency versus time plot of just a random spot on the sky. And most of the things you see on there are from well-known satellite constellations, GPS, Iridium. But we can remove that because for most observations, we're either using that 7-element receiver at Arecibo, or with Breakthrough Listen, they're pointing at something, pointing to something else, pointing back, going back and forth. If you see anything that's on in both or more than one receiver, it's obviously interference from something nearby. So we spend a lot of time working on RFI mitigation. And this is that same plot with the RFI, the obvious RFI removed, just the stuff that was in both on and off. We go through this, and there is a signal in there. Almost see the purple there, but I think you'll, it's a signal that we added. And it's actually there. So there we have a signal, one at the frequency of the hydrogen line, one at the frequency of the OH radical. And our software was able to identify it easily and not identify anything else in the millions of signals there as being of significance. So we spend a lot of time looking at plots like this. Maybe it's better in inverse, not really much better. Most of these are going to be signals that we added. This is a This is that one at the hydrogen line frequency, detected 14 times at the same frequency. So obviously something interesting. This is an example of more of what we deal with on a day-to-day basis. This was detected 6 times. You can see the little blue dots. And the probability that this would happen due to random noise events is about 5%. So it's just, typically we start with a 95% threshold. So so 5% is the minimum we want to look at. I call it, you've heard of the wow signal. I call this the meh signal. It's barely worth looking at, especially because its Doppler drift rates for those events are all over the place. Some of them are drifting that way rapidly, some are drifting that way. It's just a random coincidence. We also see a lot of things like this. I call this the signal. This was on in the one on signal for this target, and it has not been observed again because it's not on the list of things to be observed. So maybe there's something there. We're going to have to ask Breakthrough to spend a little bit more time on this target. For Arecibo observations, the back-end processing is a whole lot more complicated than it is for the observations at with Breakthrough, because we don't have on-off pointings. We're just following the telescope wherever it goes. And so we're looking, and in addition, for Breakthrough, we're looking at things that are within a couple of years of now. Here we're looking at 12 years of data. So the software is a little bit more complicated. It takes a little bit more compute power. Bruce Allen has thankfully let us borrow a supercomputer at Albert Einstein Institute, Hanover. The results of this, well, first we do our RFI removal. I won't go into the details of that. And we assign a score based on probability of actually being due to random noise. The results are thrown into a web-based interface, and it looks like I've got the URL wrong. Hopefully it's not wrong in okay. It's not going to let me from current slide. Okay, and of course, okay, so the Nebula page, which is available on our normal website, there's instructions on what to look for, but we haven't publicized it much yet because mainly we're still in the testing. So let's look at our top multiplets. A multiplet is a group of signals from anywhere in the 12-year period that is within a frequency, a narrow frequency window. And here are our top multiplets. The highest score is minus 434.07, which e to the minus 434 is the probability that you would get this just from random noise. So pretty unlikely. If you click into it, you get a list of the signals that are there. So there are a whole bunch of signals at a variety of times and wavelengths. List the scoring factors that go into them, but I'm going to back up here and point out that this column, which says birdie, birdies are test signals that we've added to our database. We're basically simulating an extraterrestrial transmitter, including its orbital motion, if it's in orbit around a planet, a rotation of the planet, orbital motion of the planet around the star, but we can look at the ones that are not birdies by clicking the no birdies. Still a pretty good score, minus 111. That's essentially zero probability. Oops, I clicked the wrong button. Okay, well, I should fix my laptop. And you see that all of these are essentially like that other one that I showed you. They're all at the same time. And right now, we haven't been penalizing signals based on being only in one observation. If a pixel on the sky was only observed once and you see a signal, we've been saying that's okay. Well, it turns out all of our signals are like that. So we probably have to add a term discounting that sort of thing. And I guess that's about where I'll stop. We've been working on nebula for years. It used to be called the nitpicker. And hopefully we won't be working on it for years more. Hopefully we'll have some, I really want to get a result paper out this fall. Questions? Yeah.
You mentioned that the bulk of the users were from the core board, setting 375.
Yeah.
Is there any idea of what happened?
I think that the initial, BOINC was definitely a more complicated system for users to use than BOINC is, or than the original SETI is. So, it may be that people downloaded BOINC and said, I have to enter three things. That's too much. Yeah. So So there definitely was an attrition there. I think a lot of our attrition over the years has been people retiring an old computer and not remembering to install it on a new one. I think that's what our 36-month average computer lifetime was. Basically, if we had stopped doing anything, I think we would have just had an exponential decay of users for 36 months. And we, years after we took an original server offline, that port was still getting hammered by people trying to connect. So I think it's just always do what's simple. Mm-hmm.
May it also be the fact that there was always other options?
Yeah, that probably has something to do with it. Although I would, we've tried to sell the idea that you want to participate in a large number of projects, and I still think that doesn't get to a lot of the BOINC users, because the agitation that they feel on not being able to get work shouldn't be an issue if you're running half a dozen projects, even if they're at very low priority. Okay.
Thank you.
So up next we have School Story Day. Steven. Are you using this?
I think so. I was working earlier.
All IT.
I don't know anything about computers, so.
He is IT.
IT jokes, everybody.
Turn it off, reboot it, plug it in, right? That's it.
Mine always breaks in a technical because then as soon as it comes around,
It works.
miraculously it starts working again. I can't prove what I did wrong.
Do I need this? I don't know. We'll see.
Yeah.
I do? Well- Okay.
It's already on.
It says it's on. I can't hear it, so I don't know. And okay, so I'm Steve. I also work with Ben. He's back at Purdue, not far from here. Today I'm going to talk a little bit about our sort of latest venture in a series of presentations at this meeting, having to do with some speculative execution or exploration of multi-dimensional space and that's generated by simulations. Very long title. I'll try and break it down to talk into a few parts. Talk a little bit about NanoHub in general and the bigger picture. Talk a little bit about how we integrated BOINC into the general or the overall simulation framework, and then a little bit about the actual speculative computing and a little couple of our numbers, which comparison of others in the room are not very large, but we hope to be growing. So for those of you who don't know, NanoHub is well, it's a website, of course, but it's a place to go for collaborative work in fields of science. NanoHub happens to do with nanotechnology. There are many other hubs, probably a couple dozen, maybe 3 dozen, that work on things like volcanoes or on and on, whatever you want to apply the technology to. We do simulation is something big that differentiates us from a standard website. People go there to explore both the science and so on, and hopefully to learn. So there's a big educational component. This is used in college level classes. There has been work done in undergraduate level or high school level as well. Here's the button. All right. Whoops, wrong way. Up, down. Okay, so as far as numbers go, I have a few here on the screen. In a typical year, we have about 1.5 million people come visit the website. We have about 175,000 people that have actually created a login and they've registered. This is important because you have to do that to actually run a simulation. You can browse the other content of the web page without telling us who you are or much about you. We have 600, a little bit more than 600 different tools, what NanoHub calls a tool, been published. These are contributed by the nanotechnology community. They're not written by the same people who do the infrastructure and the website. So this has happened over roughly 15 years. We've got up to 600. There being 600, some of them are very easy to use. Some of them are not so easy to use. Some of them require, you know, a few seconds on a standard computer to compute. Some of them may take a couple of weeks to run on a supercomputer sort of platform. So we cover the gamut. Let's see, down, okay. So why this is useful, or why it's attractive to people, both for developers and for the end user, is that it's a central location. People don't have to download software. All they need is a web browser. Developers like it because we provide the development environment. And again, they don't have to create their own environment. We provide a couple of different modes for developing graphical interfaces. Something called a Rapture interface, which is the sort of now the historical legacy platform, and also more recently Jupyter notebooks have been added. And another service we provide for that is source code management systems, and we provide typical, fairly rich Linux development environment. So how can we classify the various types of simulations? So there's three major reasons why a simulation might be executed. The first of these is the most typical, and this has been going on since day one. Basically, it's when the user comes to the website, they log in, they look at the list of tools, they have a problem they want to solve, they select the tool, fill in the input, push a button, simulation is submitted. After some varying amount of time, the result will come back, either through the notebook interface or the Rapture interface. The results will be rendered in some graphics or text or whatever, depending on what the tool developer did. What we've added to that in the last probably 3 years or so is a caching system to help us avoid rerunning the same simulation over and over and over because a whole class subscribes. So they have like 30 people in a classroom, they all sign up. The first thing they all do is go hit default and run. Well, doesn't sound like much, but we have a lot of classrooms around the world that use this. So if we can just, when you push the button, we check the cache. If the result's there, boom, you have your answer. That helps a lot. The second choice, or second method, and I talked about this a little bit last year, is the addition of the ability to do uncertainty quantification simulation. This is an add-on to the Rapture platform where the developer doesn't have to change their code one bit. We can apply a statistical variation to the inputs and through the simulation get the statistical variation of the outputs. But today, this year, I'll talk a little bit about the newcomer on the block, which is exploratory simulation. And what we want to do here is it serves a couple of purposes. One is has to do with that caching mechanism I mentioned before. If we can populate the cache even before the user requests a simulation, we can get the first simulation really fast. It also will allow, hopefully, for new technologies like machine learning to be applied to the results. And there'll be some more interesting results, hopefully in the next year, that come out of that work. So a little bit about how NanoHub is constructed and the infrastructure behind it. Moving from left to right, the users are all the way on the left, and the little images, thumbnails there represent the different tools. They connect to web browser or through web browser to the web server. We have a set of separate computers, separate than the web server, for doing the execution. There's about only 5 or 6 of these, so there's not a big resource there. If those resources are not enough, there's connection to many external resources, which include BOINC, includes Exceed, which is the supercomputer national infrastructure. We've connected to things like AWS and Azure as well. So it's all very flexible. It was mentioned earlier that everybody in the room probably knows how this works, but this is how it works for NanoHub, how BOINC is connected. So what I will mention about how we use BOINC is we're using the BOINC to Docker with a Docker image inside. This allows us to use the same workload to send it to PCs, Apples, Macs, Linux machines across the board, and it's realistically it's less work for us. So that's why we do that. The other important point is that the environment created within the Docker container matches the same environment that's available on the local execution hosts. So again, we don't have to refactor or reformulate the simulation code to run on BOINC. We can just take it natively and put it there. Okay, so how I had the picture earlier where we talked about Exceed and BOINC and Open Science Grid and a few others. So how do we do that? So on the picture here, there was, so we have four major components. There's the execution host where the user is connected. There's a submission host where all external work is piped through it, some of which goes to the BOINC server here. And of course, at the end is the volunteer computers, or volunteers and their computers. Okay, so as I mentioned, we're running BOINC to Docker, which employs Docker and VirtualBox to get sort of a homogeneous platform for computation. Okay, so the center of all of that is something called Submit, and it has many configuration parts. Whether you're using BOINC or you're using a supercomputer, we have the same requirements in the configuration. I'll touch briefly on only 4 out of the 9 or 10 or 11 that are here. The first of which is a site, which basically it says that if work comes into the submit server and we want to send that work distributed out to BOINC, BOINC is located at the BOINC server, which is the first line. So basically there's the contact information, some other descriptions about where the various executables are for interfacing BOINC to NanoHub. The second part is the definition of the tool. I mentioned earlier there's like 600 or so tools on NanoHub. Roughly half of those we can submit through BOINC. And so each of those has a simple stanza in the configuration, basically which indicates where is the executable path of the tool that you want to run. And there's pointers to additional files that are required to run that tool, which basically is the Docker container. So the Docker container has a list of files that you have to specify. We can use the same, so we have like 300 tools that can run this way, but there's only 9 Docker containers. So one container can be shared among many tools, but they all get, it's all indexed through these files. Additional to the Docker information, there's information in here that's particular to BOINC, and that has to do with the memory requirement, how long you want to wait for a job to come back, and the disk requirement. And as you might expect with 300 different applications that you're running here, there's a wide variation in all of those parameters for any given tool. And one of our issues is trying to determine what these limits should be set, how we should set them. That's the Docker container. Okay, so after all the configuration is done, how do you get from the command line where you may have your input file to BOINC, which is out there on some volunteer's computer? How do we make that connection? And that is done through the submit command, which is listed here in the middle of the screen. So it's really pretty simple. You say submit, and you tell it you want it to run on BOINC. You give it an input file, and for the 300 or so Rapture tools, the input file is an XML file in a relatively standard format, so it's easy to ship around. Not as big as the one that we saw earlier for the weather simulation, I'm sure. You also have to tell it what tool you want to run, which is basically the last line. That's fine if you wanted to do one simulation at a time, but we found pretty early on that we would be better off if we would submit groups of jobs or batches of jobs that are similar all at the same time. And so to go from submitting one at a time to n at a time is really pretty simple. Submit has the ability to do parametric sweeps. So what we do here is we sweep over the input file. So we make a list of the input files, we give submit that list of files, and iterate through the files and send them off. Create a batch of that one job at a time. Okay, so that's sort of the setup, the prelude to what are we going to do with exploratory simulation. So what we do realize is that, sure, we can take input files that we have, we can look at the XML file and realize, or we can learn that certain inputs are numeric and that they vary from point A to point B. And so what we do then is you split that range into some small number of points, and you generate a simulation for each combination of those points. And then you can submit that off. So that's all very, very straightforward and pretty simple. But the probability of the user actually later requesting any one of those points is probably pretty small. So what else can we do with this data or these simulations that we create? And as I mentioned earlier, we are in the early stages of applying some machine learning study techniques to the results that are returned. Some of the other ideas are that we can certainly perform sensitivity analysis on the results, or we can analyze for covariance of results within the same simulation. So all of these techniques and all of these methods are based on the idea of having a large data set, a large number of, in this case, simulations. So the challenge has been put to me to generate 10 million simulations in a year, or the rate of 10 million per year. And that, depending on where you're coming from, that's a big number or a small number. But to put it into context, in the 2 years that the program is probably has been running, I'm not sure we've got 100,000 jobs yet. And now we want to shoot for 10 million in a year. So that's another reason. So we have the first problem is how to generate that much work. And that was mentioned in other presentations this morning as well. Users coming to the website and hitting the button does not generate that workload. We can generate that workload for this exploratory simulation because we're basically scripting the generation of the files. And it just fits into the overall system. It's in one additional box here, which is called SpecBot, which what it does is we will basically take the Rapture files, the XML schema files, search for the scalar inputs, numeric inputs, either integer or floats, that also have defined upper and lower bounds. We can split those ranges. BOINC on a BOINC server. And the trick, the magenta here are the times at which submissions of work were done. So basically, there's a set point here, which has varied over time. So for a while, it was trying to keep 10,000 jobs, and it was 15,000 jobs, and today I'm trying to keep only 5,000 jobs. But we see we can do that. So basically, every 15 minutes, we look at this number and we say, oh, it's less than the set point, create another batch, submit the batch. So we found we hit a lot of roadblocks in trying to do this. Some of the roadblocks were BOINC related. The bigger roadblocks were related to the rest of the NanoHub infrastructure. So when we tried to submit more than about 1,000 batches at a time, we ran out of processes on Unix machine. Had the default limit of about 1024. Another common problem is disk quota. None of these jobs has particularly large amount of data, but if there's 50 to 100,000 of them floating out there somewhere, in aggregate would take a lot of space. We hit on our server machine was a 24 gig machine. We routinely max that out. And so the sysadmins monitoring the system were getting red flags and phone calls in the middle of the night. So we said, okay, we can't do that. We have to do something different. The memory. Also, we ran into a problem with basically the database system I was using. We were using SQLite, which only allowed us to process one transaction at a time. So the transaction list was a giant queue of that. It was very hard to keep up. So that most of those problems were addressed by doing two things: switching to MySQL for database, and changing the way we monitor processes so that instead of having a monitoring process for each batch, there's one monitoring process for all the batches. That took care of the memory problem mostly, and the number of processes. On the BOINC side of things, as I mentioned earlier, we have this large variation in the tool requirements. Each tool has a different requirement, and for the same tool, depending on the input, there may also be a large variation in requirements. Either typically in terms of time, some inputs may take a minute, a different set of inputs might take an hour. Everything else may be the same, and so it's hard to predict that ahead of time. And so maybe we can take maybe that's one of the things we can do with our morning processes, how we could predict this to avoid getting the BOINC time limit or disk limit errors, or memory limit errors. Okay, so that's what I have. I'm happy to take some questions.
I might be wondering about the BOINC problems. You said you have 600 tools and only 300 work on BOINC, even though you're using Docker unified environment. I'm wondering if you know what the problem is with getting these other 300.
Yeah, so the question is, we have roughly half of our tools we put on the BOINC. And is there a reason why not all of them are on BOINC? The reasons are a few there. For some, they require multi-core simulation, and that, I guess you can do small ones on that with BOINC, but we haven't explored that. Some of them require more like tens or hundreds of sort of MPI sort of execution, so that take those off the list. Some of them are off the list because the codes that we run are, I won't say proprietary, but they're limited by license and where they're allowed to run, things like that. Some of them, another thing that comes up is the combination of the software required to run the tool and the Docker container itself is just deemed to be too large. It would transmit and come back. It's much larger than the ones we do. So we've just sort of arbitrarily taken them off of this.
Two questions. So is all data that people work with on NanoHub considered to be public? There's not any kind of proprietary data that people work with there?
Okay, so the question had to do with ownership of data, if I can put it that way. It's a good question. There is when you sign up your terms of agreement, I believe in there it says that you have data and you can see it, but it's doesn't belong to you necessarily. And we can share it with other people if that's what you're doing. But there's no identity attached to the data. So if I ran something and then you got the results as well through the caching mechanism, you wouldn't know that I ran it. It would just be anonymous data.
It was more about like, if I submit a job and you run it on your server, it's just the privacy is just between you and me. But if I want to run a job and send it to your server and then your server runs on some random BOINC machine somewhere, there's concerns there, right?
For some people, sure. Yeah, so the question had to do with, I guess maybe you signed up with NanoHub and you expect your work to be done on NanoHub hardware, and NanoHub may turn around and send it off somewhere else.
Yeah.
Is that a correct characterization?
Yeah.
Yeah. Again, there may be people that have concerns about that. It hasn't really come up.
Okay.
But again, if we don't do this, I guess we should do this. We should put it in the terms of agreement. Basically say, you don't control where the actual computation happens. I mean, as the submitter of the work, you don't control it.
And the other question was the exploratory simulation, where you're basically randomizing the simulations and caching them. Is that mostly just to improve user experience, so that they don't have to, if they do something very similar to something that's already been done?
Well, yeah, so the question was about exploratory simulation and how will it benefit the user, essentially. As I mentioned, it's the way our cache works today is it has to be an exact match of your input to something that's already been archived. We hope to sort of relax that condition to say that if you ask for a simulation about some point and we already have maybe 3 points that are close to that, we could give you those 3 without any additional computation. And if you still wanted to proceed, you could actually do your simulation as well. But that hasn't happened yet, but that's another way we can use it in the future.
Hearing a little bit of a trend, I'm curious about, like, the idea that the original SETI client was really easy to install, and then kind of moving to BOINC was just a little bit more of an ask. So now the idea of seeing that you kind of now have to do like Docker and VirtualBox, do you think that impacts the ability of volunteers to participate? Did you think about whether, or have you seen any impact on that?
Okay, so the question has to do with the addition of VirtualBox and Docker. Does that complicate volunteer life?
Yeah.
And I don't think it actually does. Through the BOINC central site, you can get the VirtualBox directly from them. Docker is all of up as part of our, it's all internal to us, basically. The user doesn't know it's there. Docker runs inside the VirtualBox VM. So the client machine itself doesn't need to have Docker installed, which would bring up other issues. Yeah. Anybody else, or are we ready for break? Or whatever's next.
Yeah, not break.
Not quite.
Now break.
Okay, no break, unfortunately. But fresh tea and coffee should be coming out soonish,
I think they replaced that.
or it's already out. Okay, so we're going to go straight into the next session. It'll take us a few minutes to set up. Please don't leave though.